Okay, the title of our project was Spreading Metals in the ISM. And so the idea of our project was that we look at a simulation from a paper by Romano et al., where they investigated whether just stellar feedback could be responsible for ejecting a majority of gas from ultra-faint dwarf galaxies, quenching the star formation early. And for that, they performed simulations with numbers where the galaxy was based on the dwarf galaxy Virtus 1, which is here shown in the beautiful image from the Stone Digital Sky Survey. And yeah, they used the box size of 2 kiloparsecs. And on the right-hand side, you can see some of the results from the simulations in the paper, where on the left-hand side, there's the density, in the middle, the temperature, and on the right-hand side, there's the metallicity, and it is shown how it evolves over time. Yeah, and the idea is that we, on the one hand, we reproduced the simulations, which we did with a lower level of detail since we are somewhat limited in our computing resources. So we used the maximum refinement level of 7 instead of 11 from the simulations, which corresponds in the paper to about 1 parsec. And we also compare the simulations for cases where the supernovae deposit different energies in the galaxies.
So the first thing that we did was to run the simulation with the same initial parameters as the reference paper to see if we could reproduce the results. We saw the results of the simulation, and we have also calculated radial profiles. You can see in the first column those for density, and in the second column those for pressure. The lines in which we are interested are the black one, which corresponds to the beginning of the simulation, and the red thick one, which corresponds to 20 megayears in the adiabatic limit. If we compare our results to those of the paper, we can see that the behavior is identical except for the level of detail because of the low resolution. In the density profile, we can see how density decreases in the innermost regions by 1 order of magnitude, more or less, and the same for the pressure, in which we can see how the hot pressurized supernova ejecta expands to the outer parts.
Okay, so now I can show you a couple of nice slices. Yeah, so the video isn't running, of course, because it's a PDF. On the left-hand side, you can see the simulation with 10 to the power of 51 ergs. And on the right-hand side, 10 to the power of 52 ergs. And these are slices of the density. And in those, you can see that at this time point, 5.7 megayears, which is the longest time we could run the 10 to the power 51 erg simulation, because it took a quite long time because the time steps got really small. The bubble on the top is actually a bit larger than the bubble for the lower energy case. Oh, this also doesn't work. Okay, now here are slices of the metallicity, where you can see that we actually have a lot more metallicity right now in this ISM compared to the lower energy case. This is the temperature. So you can see that not only did the bubble spread further, but we also have a higher temperature, so likely also a higher pressure in this bubble, so it will extend further in the future. And the last one is just the radial velocity, where you can see the radial velocity is also a bit higher because you inject more energy. So yeah, and now Vanya will tell you a bit about what he did.
Yeah. In previous part, we changed only energetic of supernova explosions. And here, instead of changing energetics, I decided a bit to change initial conditions to add rotation to our galaxy, because for now it's considered like it's stable, it's not moving, and only supernova explosions and stellar wind matter. Yeah, and it's inspired with two starburst galaxies, which is Marchian 1 in NGC 2366 and this strange name, which well described in work of Penck in 2023. And here you can see that in the direction of outflow, you also see a slow increase of metallicity. And I was wondering if we can reproduce this with almost the same setup, this increase for observations, and if it will be the same. So yeah, this is Marchian series 1 in 2366. It published recently, so you can look. And his initial conditions for potential and density. I also did very dumb assumption for pressure, and velocity comes from potential. And after a bit of computations and help of ChatGPT and some amazing supervisors, Simon, Eva, and Donatella, I was able to compute initial conditions, but afterwards everything exploded because it's pretty difficult and not very straightforward how to stabilize rotating disk. So yeah, that's my results.
It's okay. Few questions?
Yeah, and thank you for your attention in every language.
How much time, what is the size of your simulations in pixels, and how much time does it take? Did you do it on your laptop?
Yes, and the maximum size is 2 in power of 7, so it's 4,000 something.
And how long does it take, the simulation?
On my laptop, it took 3 hours on 22 cores for initial condition, which is not changing, and I'm not sure what was about supernova sponge with increased energy. Have you idea? Okay, we didn't estimate time.
Yeah, thanks. I was curious about what is the assumption you made to try to find an equilibrium solution for that Miyamoto Nagai disk? What was the principle behind your equilibrium solution?
Well, I assumed that there is a long work around this field, and they made analytical solution for this profile. And what left for me is calculate mass and velocity, which is comes from mass. So very easy equation. And then I assumed thermal isothermal disk, but for some reason it doesn't work. Maybe there's some bugs. So yeah. One version of bugs when I computed mass in wrong way, and this is my best results. I have no idea what bugs there for now, and I'm going to investigate it a bit more.
Okay, any more question? No. Okay, so thank you.